Okay, I'm going to try and explain the photoelectric effect equation to you very quickly. It's essentially very simple. It's one of the fundamental laws of physics. It's conservation of energy. Okay, so Einstein had this idea that photons were quantized in packets of energy, and the energy of a photon was equal to hf. So here is the energy of an incoming photon. Now, hopefully you've had a look at the photoelectric effect experiment, and you have an idea of how it works. So you know that light is emitted on the surface of a metal. Now the surface of the metal is obviously has electrons in it, and those electrons, as we know, exist in energy levels. So let's look at this as a very simple energy level diagram for a metal. And the electrons could exist in any one of these four energy levels. We simplified it here. Now, let's just take, for example, an electron that exists in the top energy level. Just above here is the point at which the electron would be free. So it's in like a potential well, we call it. So let's say this is 0 electron volts. It's caught inside. It's attracted to the nucleus, and it's caught inside this atom, and to be free of the atom, it needs to be above this line, an energy line, up to 0 electron volts. Now, once it's beyond that, it will be a free electron, and it can zoom off and be a free particle. Now, let's think about the process of the photoelectric effect. What essentially happens is we shine light onto the surface of the metal, but we're thinking of this light as a packet of energy, as a photon, and hopefully our electron will absorb that photon, gain the energy, and shoot off. Okay, now conservation of energy. The energy from the photon is hf. Okay, the energy of the photon goes into the electron, so the electron gains that energy. That energy has to be shared between two places. Okay, firstly, it has to go into this thing, which is called the work function, which I'll explain in a second, and secondly, it goes into the kinetic energy of the electron. So energy comes in from the photon. The electron absorbs that energy. Now, first thing the electron has to do is it has to escape the atom. So it has to get rid of, or it has to use up this 5.54 electron volts just to get out of the atom. Now, that is the work function. Okay, it's the minimum energy required to escape the surface of the metal. So you can see that the minimum energy equates to the top energy level. Obviously, if the electron was here, it would need more energy, so it wouldn't be the work function. So the work function is the minimum energy required to escape the surface. And in this case, it would be 0.54 electron volts. Now, obviously, the energy that comes in from the photon, first lot of that energy has to go into escaping, so that's the work function in this case. And the rest of the energy has to go into, or any energy that's surplus, extra, goes into the kinetic energy of the electron. So as you can see, it's quite a simple case of conservation of energy. Energy in, and these two are the energy out. The electron has to use this to escape the metal. Any surplus goes into kinetic energy. Now, in this case, in the case of the photoelectric effect equation, hf is equal to the work function, which is this minimum, plus Ek. Now, Ek in this case is the maximum possible kinetic energy the electron can have. Because obviously, if the electron happened to exist here, it requires more energy to escape the atom. Therefore, the kinetic energy would be less. It would have less kinetic energy for the same energy of photon. Okay? So, in this case, it is the maximum kinetic energy of the photon. Of the electron emitted for this frequency of photon. Obviously, if we increase the frequency of the photon by changing the wavelength, then the kinetic energy could be higher, but the work function wouldn't change because the energy levels are the same. However, we could change the work function by changing the metal. Different metals have a different energy level structure. Okay, so if we look at the photoelectric effect equation, HF is equal to the work function plus EK. Just remembering that this is the maximum kinetic energy of the electrons emitted, this is the work function of the metal, and it's specific to individual metals, and this is the energy of the incoming photons. What I'm going to do, I'm going to rearrange it to say that EK is equal to HF minus the work function. Why? Well, as we always do in science and physics, imagine what I'm going to do is just write a very important equation underneath, y equals mx plus c. And you can see that it's in the correct format for a straight line. So if I was to plot a graph of kinetic energy of an electron, of electrons emitted, okay, so, but not just kinetic energy, the maximum kinetic energy of the emitted electrons against frequency, you can see that I should get a graph that looks something like this. Okay, just a straight line graph. Things to note from this graph, there's lots and lots of different things. Now, remember, this is the frequency of the incoming photon, and this is the maximum kinetic energy of the emitted electrons. Now, first thing, let's look at this point here, okay? This point of the graph, it kind of doesn't exist. We'll come back to that in a second. But if you consider, let's say I'm shining light on a piece of metal, and I'm looking for electrons to be emitted, and I shine the light with a frequency less than this frequency here, so any one of these values in this region. Will I get any electrons emitted? Well, no, because there is no, in this region here, there's nothing. There's no electrons emitted with no kinetic energy. Well, why is that? Well, think about our energy level diagram again, okay? And take that top energy level, and this is 0, or the point at which an electron will be free of the atom. If the frequency of the incoming photon, so here's my photon coming in, if the frequency corresponds to an energy, and remember that the energy of the photon is HF, so energy is HF. Now, if this frequency corresponds to an energy which is less than this gap, then it will never have enough energy to escape. So below this frequency here, no electrons are emitted, and we call that the threshold frequency. Obviously, as soon as the frequency, any value above that frequency, we do get electrons emitted, and they have varying kinetic energies. And obviously, the higher the frequency, the higher the energy of the photon coming in, so the higher the maximum kinetic energy of those electrons. Then another thing you need to know from the graph is the idea that you can calculate Planck's constant, h, from the gradient, which you can see here. Gradient is Planck's constant. And one last thing is that this is the work function, okay, of the metal. So this is an energy axis here, this is energy, and this corresponds to the work function of the metal. So if you were to plot the same graph, and you had different metals, they would have different lines. So one metal might have a line like this, one might have another one like this. Crucially, the gradient never changes, okay? But where it cuts the x-axis does, depending on the work function of the metal. And that's about it with the photoelectric effect equation. There's lots more you need to know in terms of stopping potentials and looking at the experiment itself, but in terms of the equation itself, that's pretty much it. Okay.